we continue our discussion on circuit elements. We first discussed in the last two lectures about ideal circuit elements. For example, inductor was essentially a coil of wire, and we assume that in that coil of wire there are only magnetic fields, and as a result of Faraday's law we could actually at the terminals of the wire come to a simple description of the element, where we saw that the voltage is equal to L di by dt, where L is in fact a positive value. It is called the self inductance of the coil. So, if you recall what we did some time back, just a quick recapitulation. The assumption on an ideal inductor was, with a single turn here of course, is that there are only magnetic fields here, and this portion is the black box or the inductor. And if we apply Faraday's law, we assume of course here that the fields, magnetic fields are very negligible, all the fields are within this inductor. In that case we can define uniquely a potential difference here, the potential difference, I will call this a voltage VAB, which is in fact equal to the potential difference between point A and B. And if we measure the potential of A with respect to B, and if there is a current flowing in like this, then VAB is equal to L di by dt, where I is the current flow and L is a positive constant. Now, this potential of course can be defined uniquely because we assume that magnetic fields here are small or negligible. Therefore, we can in fact define the voltage by doing E dot dl from this point to this point. We compute the potential difference between A and B, and E dot dl is uniquely defined and is not path dependent provided there is no flux in this region. Okay. So, these are the assumptions going into the definition of an ideal element called an inductor. Of course, there are very many non-idealities in this. We saw that we also defined a capacitor, an ideal capacitor, and we again saw there that there are some assumptions which are in fact made when defining these ideal elements. For example, this coil could have have charges on it, and you could have in fact electrical fields within this inductor as well, but we neglect those effects. Now, if we in fact do take into account such effects, we do end up with a more complicated model of an inductor, but in fact at higher frequencies, that is when there are larger rates of change, we have to consider the effect of electrical fields because they affect the magnetic field as well. So, what we really saw, in fact we gave an example of a practical inductor. The model of a practical inductor in fact is as shown in the figure here. At low frequencies or when there is a low rates of change, a real inductor has got some resistance in the winding. In fact, you can't pinpoint where the resistance is because there is a coil of wire, it has got finite conductivity, and there is a electrical drop along the wire as well. So, this in fact is represented by the resistor, and of course, this resistor is distributed. So, the real the correct representation would be of a distributed resistance. As we increase the frequency, there is we have to take into account electrical fields which may exist between 2 points on the coil, and this is in fact the model of a inductor. And in fact, this is not obvious, but again this capacitor being distributed all along the wire can in fact again be approximated by a single lumped capacitor. So, actually this approximation which is shown here is again valid in the low frequency range. In fact, you can what is known as make a lumped approximation of a distributed element provided your frequencies are low and the size of the elements are, in fact the inductor is not of very large size. So, you can in fact model this by lumped capacitors and inductors. This is of course a model, and it has got this region of validity. In the real sense, all these inductances and capacitances are actually distributed, a fact which we shall consider a bit more in detail when we consider a more complicated element called transmission line. So, for the time being, let us assume that this is a good enough model of an inductor, and last time we did an experiment to actually check out whether this capacitive effect can be visible. In fact, we also, before we just go and recapitulate what we did last time in the experiment, let us again go a little bit back again. An ideal capacitor was defined as an element which has got no magnetic field inside this region, and you had symmetrical charge minus q and plus q, and because of this plus q and minus q between these plates, we could have an electrical field, and of course, then if we compute this compute the electrical field from this point to this point, we assume that these leads do not have any resistance and there is no voltage drop, then in that case the voltage is obtained by again integrating V E dot dl. We assume no magnetic field within the capacitor, and this in fact gives you a relationship Q is equal to C V A B, and in fact this is actually coming from Gauss's law of electricity, that there has to, since there is an electrical field, there will of course be charge enclosed, if you surround this plate by a sphere and compute the electrical flux. So, actually you can compute the electrical field, there will be an electrical field between the plates, and because of this Q is equal to C into VAB, the current, which is nothing but the rate at which a charge flows through a cross section, is equal to C dVAB by dt, assuming that the plates are not moving themselves. This in fact this current is nothing but the amount of charge which flows through a cross section of this conductor here, and if you look at so if I can call as I here. So, this is the relationship between the current and the voltage for an ideal capacitor. So, using the basic laws of electromagnetism and neglecting the magnetic fields within the capacitor, we in fact get these equations. Now, we also of course talked about the resistor, which I will just quickly recapitulate. A conductor or any material can have has a number of charges, free charges. In fact, for a conducting material like copper, there are large number of free charges per unit volume, and these on the average will be drifting, and if you have got the drift velocity v, and in case you are looking at a cross section A, then the current is proportional to the number of charges per unit volume into the drift velocity, the average drift velocity of these charges are moving in random. Typically in a conductor which has got of course some resistivity or conductivity, which is the reciprocal of resistivity, what we see is that if the V cross B, that is the magnetic fields are small, or the velocity of the charges, the drift velocity of charges are small, in that case, and the conductor itself is not moving, in that case the current is in fact you do not have to consider the V cross B effects, the forces on the charges. In fact, the current flow, what causes the current flow is the forces on the charges. Okay. So, because of so called viscous effects, you actually have a constant flow of with roughly a constant drift velocity in case you have a voltage drop or an electrical field across the conductor. So, this we saw was represented by an equation, current density is proportional to the electrical field. This is of course assuming that V cross B effects are small. So, this in fact was the equation of a resistor in point form, and of course, we know this, the manifestation of this in the macroscopic world is V is equal to IR, which is nothing but Ohm's law. So, this is effectively the three elements which we have discussed, and what we saw in a non-ideal inductor was you could a real life inductor can be modeled as an RLC element. And last time we in fact at low frequencies we found that if you apply a sinusoidal voltage across the inductor, then the steady state current is in fact lagging the voltage, but that happens at low frequencies because the current through the capacitor at low frequencies is small. Why is it small? Because when there are smaller rates of change, we find that the amount of current is going to be less, because the rate of change of voltage into the capacitance is what is going to give the current. Now, at low frequencies this effect is very less, because in fact this capacitance is quite small. But as you go on increasing the frequency, you will find that this effect is prominent. In fact, after some time, after a frequency becomes large enough, you will find that this capacitive effect starts becoming more prominent than the inductive effect. So, the current drawn is practically through the capacitor, because the rates of change of voltage become very large because of the high frequency. Now, if you this typically happens for a real life inductor at very high frequencies, and we did a experiment last time and we saw that it was in fact at around more than 500 kilohertz or more than 70 kilohertz for a 60 millihenry inductor. So, this kind of behavior is quite interesting, because it shows that what we call as inductors and capacitors are in fact idealization of real life elements, and the region of validity of those laws, simple laws which describe a circuit element, are in fact limited to certain frequency ranges. One or two things about the experiment itself: we took a 60 hertz inductor and then we applied a voltage of varying frequency, and I mentioned to you that there are some important considerations which you should keep in mind. The current measurement device which you have should have adequate bandwidth to measure currents at a higher frequency. If you choose a wrong current sensor, wrong I mean that if the frequency response of the inductor of the current sensor is not what we would expect out of a current sensor is that it measures current accurately over a wide range of frequencies, but the current sensor itself is not an ideal element, and it also starts distorting in some ways, distorting or actually having some other effects which actually your measurement does not match what is really is there. So, you should in fact choose the right frequency, we should choose the frequency bandwidth of the current sensor appropriately. We had in fact a clamp on device. In fact, if you choose a current sensor with a wrong or rather very low bandwidth, the current sensor itself may give you phase shifts in the current, which actually distort what your inference would be. We just quickly show you that in the last class I showed you a current sensor which had very high bandwidth, but if I choose a sensor with a relatively low bandwidth. So, if you look at this frequency of this, if you look at the specification of this particular current sensor which we have, it has got actually a 100 kilohertz bandwidth. So, we can expect that slightly lower than maybe a decade below 100 kilohertz to and above, we should take the results with a bit of a pinch of salt. So, in fact, if you take this sensor and we try to measure currents which are say of 100 kilohertz or so, or greater than 50 kilohertz, we get somewhat unusual results. What is shown on the screen is when the frequency is 50 kilohertz roughly, and as you increase the frequency even further, actually this particular transient is occurring because we are changing the frequency. There is something called a natural transient which occurs which is reflected when we make a sudden change to the frequency. But once it settles down, we find something unusual happening. Yeah, can you continue? As the frequency is increased, you find that the phase shift between the current and the voltage becomes almost 180 degrees, which seems very unlikely that it is true. And when we go to a frequency of 101 kilohertz and above, what we find is that there is a 180 degree phase shift between the voltage and the current. In fact, this is not what we saw when we considered our the same experiment with a high bandwidth current sensor. Now, what is actually happening is this current sensor itself at this frequency is introducing some effects of its own. So, we see actually a phase shift which seems very unusual of 180 degrees between current and voltage, which is obviously not is a kind of spurious reading. So, one of the things which you should remember is of course that these elements, the measurements which you make, you should choose the correct bandwidth of all the sensors. Now, I have in fact mentioned here the several other things like natural transients when you suddenly change the frequency. What I have shown you here is in fact the sinusoidal steady state and not the transient response of the system. We shall see when we hook up a circuit with R and L and C elements, we have something called a natural transient as well, in addition to what we are seeing here is the sinusoidal steady state. If we actually take a similar kind of frequency response analysis of a capacitor or a resistor, can we go back to a resistors? Yeah. A resistor in fact also has got such an equivalent circuit. In fact, we tried to do it frequency response of a 60 ohm rheostat, which is actually wound on a in a solenoidal fashion. Yeah, can we just show that? Yeah, and we did a similar experiment. We'll just skip a bit because the experiment is practically the same as before. What we will see is that as we increase the frequency beyond a certain point, we will first show this is the voltage and current as expected are in phase, but if the frequency goes beyond a certain point, this is now greater than 100 kilohertz, you will find that a sudden phase shift between the current slowly starts appearing. This is of course a natural transient, now it settled down and we shall see as the frequency increases. Now, this is really high frequency, this is around 500 500 hertz and well, this is not that high a frequency. And as we go beyond 1 kilohertz, we actually see a phase difference appearing between the voltage and the current. So, this is not surprising considering the fact that these are non-ideal elements. If you look at the right in the beginning of this video, can we go back to the beginning of the video? Somewhere right in the beginning where we show the rheostat. Yeah. A rheostat is of course made out of wire, wound wire, and this in fact has this inductive effect. It is almost like a solenoid, but this inductive effect, the resistive effect is predominant. The inductive effect is starts becoming apparent only at higher frequencies. One point which we should also remember is many of these instruments like this storage oscilloscope, digital storage oscilloscope is of course is based on sampling the waveforms and then plotting them. You should choose the sampling frequency high enough. If your sampling frequency is not high enough, you may end up with another spurious kind of effect called aliasing. For example, if you are measuring a sinusoid which is of a certain frequency, but your samples which your device is only measuring it at instants, you are getting samples of this waveform only at these instants. So, you are getting this value here, this value here and this value here, and if you interpolate between them, that is what you do while plotting, you will get a spurious inference that this is in fact a sinusoid of much lower frequency. This effect is called aliasing. What you of course need to do is take a lot of samples, which is of course related to the frequency of the wave which you are trying to measure. If you do that, of course, then you will get the correct inference. I am sorry, yeah, you will get the correct inference if you interpolate and so on. Okay. So, if you choose a sampling frequency which is low, very low, you will actually see an effect called aliasing. In fact, if you, this is also seen in sometimes in movies where you are watching a wheel which is rotating, usually a car wheel, and in case the speed of the vehicle becomes high, at some point the car wheel seems to become stationary and in fact reverse in direction. This occurs also because of aliasing, because you are sampling or in fact taking discrete images of the car in a movie, and if you take these samples at a very low frequency, low frame rate, and the wheel is moving at a high speed, you get an effect as if the wheel is stationary or moving at some other speed than it actually is. So, this is also an example of aliasing. For example, you have got a wheel which is rotating, and suppose I have got an X mark here, and I take a photograph of the wheel at this instant, and the next photograph I take, the wheel has reached right up to this point. It has gone around and come to this point here, and the third snapshot I take, the wheel has gone from this point and come up to this point. Now, what inference will you draw? You could actually be thinking that this wheel is actually rotating from this to this to this, that is in the opposite direction at a, so this kind of wrong inferences can be there. So, you should remember that in case you are using a digital device which is doing sampling, the sampling rate of the device also should be chosen to be adequate. We had in fact chosen a high enough sampling rate, so we did not get any spurious results on this account at least, but this is something which you should be aware of. Another thing is, if you are taking samples into a storage oscilloscope, it may be doing some kind of signal processing. For example, you may be removing any DC offset from the waveforms, or you may even be filtering it. So, this itself may cause some effects which may be very serious in some situations. So, it is important to be aware of these effects and how they affect the measurement. We also try to take the frequency response of a capacitor, and we will not be showing you this, but the capacitor, where as we increase the frequency, we found that in fact it does not give any in the range 1 to 500 to 600 kilohertz which we tried to measure here, we could not see any unusual effect. The capacitor behaved just like a capacitor. So, in fact, the capacitor behaves like a capacitor for a very large frequency range, at least the kind of capacitor we saw. So, can you just show the capacitor which we did our experiment on? Yeah. So, we used a capacitor which is shown here, and that was 1 microfarad. So, I will just quickly go show you there. Yeah, this was a 1 microfarad capacitor, and in fact, when we tried to do the experiment on this, we could actually see at least in a very large frequency range, the capacitor indeed behaved like a capacitor. So, the capacitor behaves like a capacitor for, at least this capacitor behaves like a capacitor right up to 1 megahertz. It predominantly have a capacitive effect. We do not see any major non-ideality there. Now, coming back to what we were saying just a few moments ago, one of the interesting things which has been discussed in the Feynman lectures of physics is a real life capacitor. Of course, at extremely high frequencies, the rate of change of magnetic field within the capacitor may in fact affect the behavior of the capacitor. This we did not see in the frequency ranges 1 to 1 megahertz, at least for the capacitor which I just showed you some time ago. But this effect would be there eventually at some frequency. The reason is, of course, a changing electrical field also causes a magnetic field. Why is that so? Because of Ampere-Maxwell's law. So, if you take a capacitor, there is in fact, whenever you change the electrical field, a magnetic field is there. So, there is in fact even just like as I mentioned in a inductor, there are capacitive effects. You may in fact have these magnetic effects within a capacitor, but these are evident only at extremely high frequencies. So, this normal capacitor which you see behaves like a capacitor for a very large range of frequencies. So, this capacitor, in fact a real life capacitor, if you look at the photograph of a real life capacitor, can you show that? This is, of course, these are the capacitors which you normally come across. These are small capacitors. You also have electrolytic capacitors in which there is a electrolytic paste in the capacitor, and if in fact you cut away, make a cutaway section of a dry electric capacitor, dielectric capacitor, we do not really see parallel plates. What you in fact see is a thin foil of metallic foil, and it is separated by a very thin dielectric, and it is all coiled around. So, our in our imagination we think that a capacitor would only be a parallel plate capacitor, but effectively any metallic two metals which are separated by a dielectric will have this capacitive effect. In fact, even as I mentioned some time back, a real life inductor also has a capacitive effect, because there is separation of the metallic wire, parts of the metallic wire, which are then separated by some dielectric or air or some other material. So, this is in fact how a real life capacitor looks like. A real life inductor, of course, is made out of, if you go to the previous, is usually a wire round on a bobbin, and you have what is known as a ferromagnetic core. The reason why you use a ferromagnetic core, of course, is that the amount of magnetic flux density for a given amount of current can be much higher in a ferromagnetic material, because the relative permeability is very high. Because of this, you find that most of the magnetic field is in the path where there is ferromagnetic material, and little of it goes outside. So, the ferromagnetic material also kind of routes the magnetic flux density, and little of it, of course, goes into the air as well, but most of it, most of the flux density is in fact in the ferromagnetic material. Now, because of this, one important thing, of course, is that ferromagnetic material itself, if it is made out of steel, what is known as electrical steel, then in that case you will find that there is the electrical steel itself is a conductor. So, as you in fact have a changing magnetic field within the this ferromagnetic material, you may have currents induced because of Faraday's law. There is an electrical field, and the electrical field in a conductor will cause drift of electrons. So, that also causes current flow. So, you may have a slightly complicated scenario in a inductor made out of ferromagnetic material, where there is current flow in the core as well. We try to minimize that by using laminated cores or using material like ferrites, especially at high frequency, which have low conductivity. One important thing which of course we shall consider a bit later is that a real inductor also, this relative permeability, although I have spoken of it as if it is some kind of constant, it is a kind of model of the ferromagnetic material, which takes into account of the fact that all the magnetic moments within the material, because of atomic currents, align as you apply an external current, I mean in the vicinity of an external current. But of course, if you the external magnetic field producing current, if it increases in a ferromagnetic material, the flux density also increases, but after a point the increase in the external current, or what we call as magnetomotive force, and the flux is not linear, and many of the ferromagnetic, in fact all ferromagnetic materials will saturate at some point. After it saturates, the change in the magnetic field due to a change in the electrical current which causes this magnetic field, external current which causes this magnetic field, will not enhance the magnetic flux as much as it would before saturation. So, this is an important practical issue in the design of inductors. Remember, if you use a ferromagnetic material, you can make an inductance of a relatively smaller size. The same inductor, if you try to make with the air core, you will have to, the size of the inductor becomes very large, and this also the flux kind of the path in which the flux flows in an air core inductor is much more kind of expansive, whereas in a ferromagnetic core the path kind of gets defined, the flux tries to go in the path defined by the ferromagnetic core. So, these are some of the interesting points relating to practical inductors. We will come to practical inductors and transformers a bit later again. When we look at other kinds of devices, we will actually take a break of talking about circuit elements. If you look at, there are other kinds of devices, can we just like cables and transmission lines. I did mention some time ago that an ideal inductor having a relationship VAB is equal to L di by dt, and ideal capacitor having the relationship the current being equal to C dV by dt are in fact in real life there are magnetic fields as well as electrical fields both in capacitors and inductors, and the other thing is that it is these kind of effects we normally can neglect in certain frequency ranges, and also when the size of these elements are relatively small, the geometric size. In fact, in most in all in fact real devices there are both magnetic and electrical fields, and in fact they are distributed. As I mentioned some time back, the resistances and the capacitors in an inductor in fact distributed, and these distributed effects are more prominent at higher frequency, and also when the you have got this devices spread over large geographical extent, and this is something we will learn a bit later in transmission lines. In transmission lines you would have to consider a distributed model of an element. In fact, this holds also for a cable, and although the electrical and magnetic fields in a transmission line, a two-wire transmission line at low frequencies, we can again idealize the kind of transmission fields, but still you need to have a kind of distributed parameter model if you want to study a transmission line. So, a transmission line is a distributed parameter device where you consider the distributed effects. So, an inductor which we saw some time ago is also a distributed parameter device, but its inductive effect is very prominent, and at low frequencies especially you can practically treat it by a simple control law, and we can talk of macroscopic and lumped voltages and currents, lumped and macroscopic definitions of voltages, currents. If you take a transmission line on the other hand, the current and voltage of this transmission line cannot be uniquely defined as the current at the terminals, because along the wire the currents and voltages can be significantly different. So, because of this we will have to try to understand this whole device, this transmission line and cables, especially when the lengths are large, by a more complicated model consisting of both inductances and capacitances. At even higher frequencies, which we normally do not encounter in electrical supply systems, we may have to consider more complicated fields which cannot be represented by simple capacitors and inductors. We are not going to discuss this in detail, but I just want to for you to remember these points, so that later on if you intend to become a communication system engineer, you may need to understand that the electrical fields and magnetic fields cannot be described or modeled like simple capacitors, capacitances or inductance or combinations of them that easily. So, this happens in devices like waveguides, resonators and antennas. In fact, these kind of devices, the electrical and magnetic fields can be quite complicated, and in fact, it may be difficult to represent these devices. In fact, one does not represent, for example, one cannot represent the effect of an antenna simply merely by capacitive and inductive effects, not even distributed capacitive and inductive effects. One of the interesting facts about Maxwell's equations is that a changing electrical field causes a magnetic field, even if there are no currents. In fact, the Ampere-Maxwell law, which if you could just if you could have the Maxwell's equation shown again. If you look at Ampere-Maxwell's law, the second term here on the right hand side indicates that even if J is 0, that is you have got a region when there are no currents flowing, in that case also a magnetic field can be caused if there is a changing electrical field. And if you look at Faraday's law, this of course we know that a magnetic field changing causes an electrical field. So, actually an interesting thing about antennas, so if you look at fields around a dipole antenna, you will find that even in a region where there is no electrical or magnetic fields, you will find that these of course what I have shown you are the electrical fields of around a dipole antenna where the charges plus q and minus q are oscillating. So, I will just show this plus q and minus q are actually moving, they are coming close to each other and then going apart, coming close to each other and going apart. The electrical fields, in fact this is a figure of electrical fields around an antenna, and what we in fact see, which is not of course apparent from this figure, is that the electrical and magnetic fields thereafter support each other even away from the antenna. The changing electrical fields cause a magnetic field and the changing magnetic fields cause an electrical field, and these kind of self sustaining and they kind of emanate outside the wire. So, this antenna in fact radiates it radiates electrical and magnetic fields. In fact, energy is also radiated out of this. The reason why this happens is that even in regions where there is no charge or current, the changing electrical and magnetic fields sustain each other. So, if you have got an oscillating charge, a dipole, that is a plus or minus q which is oscillating, you will see that this the electrical magnetic fields kind of emanate from this and they sustain each other in regions far away from this dipole through the effect of changing electrical and magnetic field. So, the changing electrical field sustains the magnetic field and changing magnetic field sustains the electrical field even in regions where there is no charge or current. So, in fact, it is more like the electrical fields kind of emanate like a person who is smoking and creates these smoking rings. So, these kind of smoking rings move away from the source. So, in fact, this kind of effect is seen, and this of course is these effects are visible only if the dimensions of the antenna are large enough, in the sense of if the charges are oscillating at a frequency f, then if the dimensions of the antenna, dimensions of the, or rather the area in which the length in which these charges keep on oscillating should be comparable with the wavelength, which is nothing but c, which is the speed of light divided by f, which is the frequency. So, at 50 hertz of course, these effects are negligible. In fact, the 50 hertz transmission lines or elements hardly radiate anything. So, in case although this effect is interesting, many of these radiation effects are not of consequence in 50 hertz systems, except when because of some reason you have got for example, when you have got lightning or sparking or corona which occurs on the periphery of a high voltage conductor. Only in these cases you have very high frequency electrical rates of change, the change of magnetic and electrical field, which can cause radiation. But in normal circumstances, for the kind of electrical supply systems we have, we hardly have any radiation. Now, one more, now we move on to a topic which we have been, in fact, all these topics to some extent have been covered in your high school introduction to electricity and magnetism, as well as in the first year of your degree course. But I hope this kind of discussion helped you to refresh and also brought out a few subtle points. We need to of course come back now to the ideal circuit elements. We will again come back to transmission lines, which are in fact distributed elements. Can we go back? So, in most of our discussion in this course, we shall consider lumped elements, and also lumped elements are in fact inductors, capacitors, resistors, and also distributed elements, but the distributed elements which we shall understand are in fact elements which can still be represented by reasonably simple electrical and magnetic fields. We shall not consider complicated effects like radiation or situations where you cannot easily model these things by capacitances and inductances. Even a transmission line can be modeled by capacitances and inductances, but you may have to use a distributed parameter model, and this is important in case you are talking of longish transmission, longer transmission lines. So, these effects in fact we will be consider a bit later. So, let us get back to something which we have already discussed, that is the Kirchhoff voltage and current law. These Kirchhoff voltage and current laws are in fact again got from Faraday's from Maxwell's equation. In particular, Kirchhoff voltage law we discussed some time ago was in fact a manifestation of Faraday's law. The statement of Kirchhoff voltage law is somewhat like this, that the sum of voltage drops along a loop is in fact equal to 0, and this actually emanates from Faraday's law, which states that circulation of E dot dl in a closed loop is equal to 0 in a loop in which there is no magnetic field. In case there is a magnetic field which is changing, in that case of course there is a kind of E dot dl, the circulation of E dot dl is not 0. So, can we just go back to Faraday's law? We will now consider circuits which use these idealized elements. So, if you look at Faraday's law, it simply says that E dot dl along a closed loop is equal to minus d by dt of B dot ds. So, if you take any closed loop in space, remember the E dot dl, the integration, this E dot dl formula which is there or law, Faraday's law, is valid for any loop in space. It is not necessary that the loop should be along a conductor or within a conductor, it can be any loop in space. So, that is an important point which you should remember, although when we talk of circuits, we shall actually be considering mostly these loops to be within the wires. So, we will be forming loops of wires and lumped elements like capacitors and inductors. So, if you in fact have a closed loop and if you have got a changing magnetic flux here, then of course Faraday's law would say that E dot dl is equal to minus dB by dt integral B dot ds. In case this is 0, then E dot dl is equal to 0. The integration of course is the line integral around a closed loop. In case E dot dl is 0, then we can define what are known as potential differences. In fact, you can talk of a E dot dl evaluated from for a finite length is also called a potential difference or voltage, and therefore, Kirchhoff current law, or in fact voltage law would actually be defined as the sum of voltage drops in a loop is equal to 0. In a real life, you can, if you are making a loop and there is a current flow in the loop, there will be a magnetic field. We call this, because of the change in magnetic field, you will in fact have a B dot ds changing. But if this magnetic field is small or the rates of change are small, we can neglect this effect. But in case you want to consider this effect, then you will have to just add to the Kirchhoff's voltage law an additional term which represents this effect. This is in fact also a stray inductance. There is a stray inductance effect which you may or may not wish to take into account depending on the extent it affects your circuit. Okay. But in real life, any loop will in fact have a stray inductance because of the fact that there is a magnetic field. When we are looping together idealized, so what our circuit analysis in fact will consider idealized circuit elements connected in a loop, and we will apply Kirchhoff voltage law. In addition, Kirchhoff current law is based on the charge continuity equation, which states that the total current flux in a closed sphere or closed surface is equal to the charge build up within it. Now, if we assume no charge build up within a closed surface, then we can say that the current entering is leaving that surface, or the total current entering is leaving the surface, which is in fact Kirchhoff current law. So, again, if you are talking of current flow only in tubes, say the conductors, let us say outside there is no current flow, but there is a current flowing in here and flowing out here, then you can show that I1 is equal to I2 plus I3 plus I4, because there is no charge build up here. In real life devices, of course, there could be a charge build up, and if there is a charge build up, there will be a kind of a capacitive effect, because there will be an electrical field drop here. So, there is a what is known as a stray capacitance associated with every part of the system as well. But if this effects of the the amount of electrical field due to this or rather the amount of charge accumulating on the at the node, for example, here is very small, we can neglect this capacitive effect. So, remember that all circuits will have these capacitive, stray capacitive and inductive effects, but if you neglect their effects and consider them to be very small, this is true in fact if the extent of your circuit is not very large, it is a small circuit in a small region, and the second thing is the rates of change are not very high. If this is true, then we can assume that we can neglect the stray inductive and capacitive effects, and in that case we can treat Kirchhoff voltage law and current law to be true in this approximate sense. Now, what we if we put together a circuit, a typical circuit will have something like a battery and elements connected in a loop. If we neglect the stray inductances and the stray capacitance, we can apply KVL and KCL in this loop or another loop. These devices in fact could be resistors, inductors, capacitors, and when you apply, of course, Kirchhoff voltage law, for example, you have to define voltage drop or rise, because you need to be aware of the signs which you are considering. In this particular loop, this is a voltage rise, that is we have considered a potential rise and not a potential drop. So, E dot dl is here is in fact in this V indicates a potential rise, whereas here we have considered a potential drop. So, if this is V1, this is V2 and this is V3, these are voltage drops, then V will be equal to, or we should say V minus V1, V minus V1 minus V2 minus V3 is equal to 0. So, this is the this is how you will apply the Kirchhoff voltage law. We need to be a bit careful about signs. I have not been very careful, or we have not discussed these very much in detail, but remember, if you take a inductor which may be consisted of more than one turn, remember that the voltage law V is equal to L di by dt, L is a positive number. In fact, L turns out to be a positive number when you apply Faraday's law with the appropriate rules. When you compute the flux and apply the right hand convention consistently and correctly, you will find that if this is the region where the inductor is and there is hardly any magnetic flux here, so we can define a potential difference here, then this L turns out to be positive if voltage is defined in this way. This arrow on top means this potential with respect to this potential, or if there is so the electrical field measured E dot dl is measured from this point to this point. So, so this is called the voltage here, or we can say V is the voltage drop in the inductor in the direction of the current, and if you actually this L turns out to be a positive number. So, this is a thing which you can try to check that L of course depends on the geometry of the inductor, it depends on the areas, the length of the wire and so on. So, this essentially depends on the geometry and the material, of course, if you got a ferromagnetic material or a just free space or air inside. So, this in fact is the convention. We also saw for a capacitor the voltage drop, that is the voltage potential of this point with respect to this point, or E dot dl measured from this the integral measured from this point to this point is in fact equal to dq rather dq by dt is equal to C dV by dt, and this is called a current. Of course, we are talking of lumped situation. So, all these are macroscopic quantities. Current is in fact the average, depends on the average drift of charges in this conductor. Now, the C again is a positive number. So, this is a voltage drop. Similarly, for a resistance, remember that this is the current and this is the voltage drop. So, when you are applying Kirchhoff's law, this is the kind of what you call you should be aware of the signs of voltages and currents. Of course, we did mention mutual inductances. In mutual inductances, you can have negative signs for mutual inductance. In fact, let me just recapitulate. If you have got two coils, just for the time being, let us assume these are single turn coils and another coil here, and you are measuring now in fact the current in this coil causes a flux in this coil. So, you have a voltage drop here because of this current flowing here. Okay, and similarly, if you have got a current flowing here, you will have a voltage drop here because there is a flux caused by this current in this coil. So, this is known as a mutual inductance effect. An interesting thing about this effect which you may try to prove is that the mutual inductances in fact come out to be equal. What is mutual inductance? The thing which relates or the quantity which relates the voltage created on coil 1 due to the current in coil 2. Okay. Now, so in fact, the voltage in coil 1 is not only due to the self inductance what we called L, but also the mutual inductance multiplied by the rate of change of current in the other coil. Okay. An interesting thing is that this M, so voltage is dependent on L and M and the rates of change of current in both the coils. But importantly, unlike self inductance, mutual inductance can be negative depending on how you measure your voltages and currents. If you have got two identical coils and they are just one below the other, so I will just, they are not actually touching here, I mean there is no connection here, I am just trying to show that they are close to each other and they are seeing more or less the same flux, then VAB and let us say VCD here, if you take the direction I1 and I2, so they are exactly similar, they are wound in a similar fashion, they are just one below the other. In that case, VAB is equal to a positive number into dI1 by dt, where the current I1 flows here, plus M dI2 by dt. In this case, M in fact comes out to be positive because the flux which is seen here is the same as the flux which is seen here, almost same direction, and you are measuring the sense of the coil is the same and you are measuring voltage also in the same way, the top point versus the bottom with respect to the bottom point. So, the same in fact comes out to be this positive sign in this case. This is L1, this is L2, and this is yeah. So, remember that in this case, sorry, there should be 1. In this case, not only is these constants come out to be equal, but in this specific case they come out to be positive. If you have got the same situation, but this is wound in the opposite direction like this, and I call this as C and D, A and B. In that case, the mutual inductance, and you are again measuring voltages in this fashion, then the M will come out to be negative. So, if you are again having VCD and VAB and the current directions to be like this, then the correct relationship will have M coming out to be negative. So, this is an interesting thing which you can verify. So, this actually sets the stage for understanding circuits using as a looping of various elements, and the simplest one of the ways you can understand a circuit or one of the simplest circuits which we can understand is this one. In this circuit, if the current is flowing here, the same current flows into this inductor, and if this is the voltage rise caused by a battery. Now, I just wish to talk about sources. A source of electromagnetic force, a source of EMF or electromagnetic source could be a battery or something which causes charge to be separated. So, that could be also, so charges feel a force if there is an electrical field. An electrical field is caused when charges are separated, or if there is a changing magnetic field, that also causes an electrical field. So, you can have in fact something here which causes an electrical field. So, there could be something with there is a separation of charges like in a battery, because of chemical reactions the charges get separated and that causes an electrical field. Once you have an electrical field around this device, so you got this electrical field around this device, the conductor, as soon as it sees the electrical field, the charges within it move. So, this kind of is the effect of the electrical field. So, a battery is a source which causes an electrical field by separating charges. Machine, you can have rotating machines in which there is a changing magnetic field and that causes a electrical field, or you can have forces created because the charges are themselves moving in a magnetic field. So, you can have a changing magnetic field or the charges moving in a magnetic field. Both of these things causes electrical field or forces due to a magnetic field. So, these are the sources and these effectively also cause electrical fields in certain areas. And once you apply Kirchhoff's voltage law, so all we have to do in this case is to write the equation. Once you have got an electrical field, of course, you can define what is known as a voltage rise, and you will get V is equal to, or better still write it as V minus IR minus L di by dt. These are the voltage, this is a voltage rise, this is a voltage drop, this is a voltage drop, this is equal to 0, because it is a voltage drop and a voltage drop, and this is a rise, this is positive, negative voltage drop, and this is a voltage drop. So, this equation is in fact can be written as L di by dt is equal to minus IR plus V. So, this effectively is a equation which we get under these circumstances. In the lecture so far, I did talk about exciting an inductor using a sinusoidal source. In fact, we did an experiment of that kind where we actually gave a signal generator created a sinusoidal voltage, and we observed the current and saw the phase shift between current and voltage and inferred whether we are seeing inductive effects or capacitive effects. Now, there we assume that if I apply a sinusoidal voltage, I will get a sinusoidal current, and when I apply a sinusoidal or whenever there is a sinusoidal current, there is a sinusoidal voltage as well. This of course is true for the circuits, the elements like inductors and capacitors, but one small point here which needs to be understood, that when you have got these resistances, inductances and capacitances which are always present, there is something called a natural transient and a forced response. A sinusoidal input to elements like capacitors, inductors or combination of them causes a sinusoidal response in steady state. There is in fact an initial transient which is called a natural transient. So, my aim in the next lecture is to try to make you correlate these transient effects and also the sinusoidal steady state effects. In this circuit which is shown in this figure here, I have considered a constant voltage source, okay, but you can have a time varying source or time varying source of electrical field, which in fact causes the flow of charges and currents in this circuit. So, we can in fact have any kind of you can in fact have ramp sources which there is a ramp of voltage or a sawtooth voltage and so on. But of particular interest is sinusoidal voltages and DC voltages. An interesting thing about sinusoids and DC voltages is that the steady state response of RL and C kind of circuit consisting of these elements is in fact also going to be sinusoidal in steady. So, if you excite it with a sinusoid or a DC, then you will get DC and sinusoid in steady state as well. Although there could be of course phase shifts etc., the wave shape is still sinusoidal. So, that is one of the interesting things about linears. This is if you have got circuits in which L, R and C are constants. I mentioned some time ago that real life elements are not like this. In case for example, an inductor is made out of ferromagnetic material, if the currents cause fluxes which are greater than what is known as the saturation flux density, you will find that the inductance value changes, or in other words the flux current relationship is not linear any longer, and we cannot strictly speaking treat it as a constant inductance. But in cases where the inductances, resistances or capacitances are constant values and do not change with the magnitude of the current, one interesting thing about circuits with DC and sinusoids is that the steady state response is also DC and sinusoids. That is a very interesting, because once you are sure of the wave shape, you can also later on design electrical equipment, because you know the kind of wave shape which will be there. If you for example, excite a RLC circuit with a square wave or a triangular wave, the resulting current will not be in steady state as well, not be of the same wave shape if you have got inductors and capacitors in the circuit, and that creates a bit of a problem, because if you have got the wave shape changes, you may have to redesign some aspects of your load or whatever you are using the electricity for. These of course circuits which I have shown here are just for the sake of understanding, but eventually you would need to use this electricity in an electrical supply system to do some work or do some useful, for example, it could be powering up a communication equipment or a lamp or a computer or a heater or a motor and so on. So, when you need to design these equipment, you of course need to know the nature of the waveforms which are going to be applied to it, and the nature of waveforms which are going to apply to the equipment. If you are using sinusoidal sources or DC source, you can be assured that the waveform which you will get, the voltages as well as currents which will flow into the device are again going to be sinusoidal or DC in steady state. This of course, I should mention here that I am talking of sinusoid of one sinusoid of a certain frequency. Of course, if you are a mixture of sinusoids, you again end up with the same problem. In fact, a periodic non-sinusoidal waveform can in fact be broken up into sinusoids of various frequencies. What I am trying to say is that it makes a lot of sense to have a single frequency sinusoidal source or a DC voltage source, because the waveforms more or less get preserved, and therefore, you can in fact design your equipment because you know the kind of waveforms you are going to encounter. So, in the next lecture, what we will do is understand the behavior of the circuits, of simple circuits, and very importantly understand transients. As a concluding note to this lecture, let me just mention one interesting application of the experiment which we did right in the previous class, and which we also touched upon in the beginning of this lecture regarding frequency response. Now, one interesting application of frequency response, that is, if you, one thing we saw in our frequency response of an inductor, we applied a sinusoidal source of different frequencies, and we saw the behavior of the inductor changed from inductive to capacitive. Now, what are these capacitances, capacitive effects of inductor dependent on, or the inductance also dependent on? It depends on the geometry of the inductor. Now, in case, because of in a real life situation, if you take an inductor or in fact a mutually coupled device like a transformer, and because of some reason the geometry of the coils changes, and you will find that the capacitance and the inductances of this circuit will change. For example, if you look at the distributed parameter model of an inductor, can we go to that? Yeah, like this. these capacitances are in fact dependent on the geometry of these coils. So, if there is any displacement or if there is any change in the geometry, in that case you will find that the values of the capacitors which you are using to model the electrical field effects within the inductor, they will change. And in fact, for example, if you find at one point of time your inductor, you did an experiment and you found that an inductor behaves like the capacitive effects start becoming dominant at a frequency f0. And after a few years you do the same experiment on the same inductor and find that it is these effects, the capacitive effects become or the circuit becomes capacitive at a different frequency than f0, then you can infer that something in that inductor has changed. And that is one interesting way of knowing that there is some problem within the inductor. Of course, you may say that I can open up the inductor, but that really means that you will have to unwind the inductor and see what has happened, or or at least it will be difficult when you have got a huge number of turns to actually check what has happened. So, in fact, in real life transformers especially, the transformer windings are within a tank, and these transformers have a working life of 15, 20, 30 years. And in case there are some large faults, that is large currents flowing because of some short circuits in the system, we will consider what these faults are a bit later, but just let us take it for now that these faults cause a large currents. These may cause forces within the conductors which cause the mechanical displacements of the windings within the transformer of this mutually coupled circuit, which is the transformer. And if that happens, then you will that may actually make the transformer a bit vulnerable, because once the coils shift with respect to each other, while they shift they may cause abrasion of the insulation between the windings, and that may actually cause what is known as the current flow in the windings, like what we show as capacitors here in this diagram here. You may also have a resistive effect there, that is some current flow may start flowing from one of the turns to another turn, that is called a turn fault, and that may damage the transformer. So, it is important to know whether there has been any physical displacement due to faults, etc. And one of the ways to do it is to test the transformer without opening up the transformer, okay, because the transformer is usually in oil for cooling as well as insulation. So, this whole setup is in oil, you do not want to take it out and try to analyze it that way. You can actually do some tests on the transformer, these same frequency response tests, and find out whether there has been a change in the characteristic frequency at which for example, the transformer turns from inductive to capacitive. So, if you in fact look at a typical frequency response of a transformer, you will find that this is the frequency response of the admittance at one of the ports of the transformer. One is a Y port and a delta port. We will understand what these things mean a bit later, but you will find that there are periods in which there are ranges in which the admittance becomes low, high again, low and high. In fact, these are all resonance points, that is something we will learn a bit later. These are points at which the transformer response at the terminal becomes capacitive to inductive or inductive to capacitive. And if these frequencies change, that means that there has been some physical displacement of the coils within the transformer, and this is one, and that may endanger the transformer, as I said, because the insulation between individual turns may break down, and that may in fact cause heating, local heating, and in some cases this kind of is a compounding effect, and the whole transformer gets damaged because all the turns get shorted, and the current, instead of flowing in that circular path, starts flowing between each turn, jumping across turns. So, this kind of effect can be actually diagnosed by this frequency response analysis. So, this is a very interesting aspect of something which we try to look at theoretically about modeling an inductor at high frequencies, but it has got some nice practical diagnostic application for transformers, in which by actually computing the frequency response, we can compute how much this whether the coils have got displaced or not. And that is, if you have already done this test on a transformer and you do it after 10 years and you see that there is a difference, that would really mean that inside the transformer something has changed. So, this is a good diagnostic tools which is actually used in practice in many utilities which supply electricity. So, on this practical note, let us end this lecture, and in the next lecture we shall see transient response, especially things like natural response of circuits.